Let us start this lecture with a thought process from Henry Ford. My best friend is the one who brings out the best in me. And in the last lecture, we basically derived the expression for mass flux rate from the droplet surface or from the droplet, right, and looking at little further how we can use it for determination of droplet burning rate, and then we will be looking at also the droplet burning time, right. So, if you recall that it is very important to estimate the droplet burning time. Why? Because when you are designing a combustors, you should see that all the droplets should be all consumed before it is going out of the exit of the combustors. Otherwise, it will be a problem in the not only the emission, but also the energy inefficiency and other things. So, and as I told, it is essential for designing combustor. For complete combustion, residence time, right, must be greater than the lifetime of the largest droplet in the spray, because you may say, look, there are several droplets. What you will be considering when you are designing? You will say, whatever the largest droplet is there, I will have to design for that, and if that is taken care, then rest of the things will be taken care, right. And this is of course a little ad hoc kind of things, and but that is essential to be using this as a design tool. And factors that dictate the residence time of the droplets are basically what? Like the airstream velocity, right, which we have not considered, and we will be considering it, and droplet velocity, and fuel injection angle, and combustor geometry, all those things we will be taking. So, if you look at the continuity, you will find out the mass of this droplet, okay, is basically consumed. So, therefore, it is getting receded, the mass getting, therefore, I am putting it negative, is equal to the mass of the fuel which is getting out outward, it is moving out from the flame surface. And this is basically equation 1, and keep in mind that this MD is the mass of spherical droplet. Right, which is changing with respect to time, because the radius will be changing, therefore mass also will be changing. And I can write down that MD is nothing but your mass will be rho L into V, right. Rho L is the density of the fuel or the liquid fuel, and V is the volume of the sphere is pi dq by 6, right. And as I told, the D is basically the droplet diameter at any instant of time, right, at any instant of time, and it will be changing, isn't it? The diameter will be changing, it will be receding. So, now what we will have to do, we will have to connect these things and recall that we had derived this expression m dot double dash f is equal to rho alpha divided by Rs is equal to ln plus V. Now, from this I can find out what would be the m dot f, because we will have to find out m dot f. M dot f is nothing but your rho alpha by Rs. What I will do? I will have to just multiply the surface area, isn't it? 4 pi Rs square. This will cancel it out, and what you will get is basically rho alpha, right, 2 pi d, right, and ln b plus 1. That is the thing what you will be getting, right. And this is RS is will be changing also, right, it is changing, right. So, therefore, this will be 2d, 2 pi d. And what we will do, we will combine these equations, right. If I will do that, what I will do, I will use this equation 1 and 2 and 3, right. I will get basically I can write down here m dot this thing is equal to minus d m d by dt, and this is nothing but here rho L pi by 6 and 3 d square d by dt, right. So, this will cancel it out, and this pi will cancel it out that side, and anything else will cancel it out, and the d also will be cancel it out, this d will be cancel it out, yes or no, 1 d from this side to that, right. Then you will get, I can write down that d by d by dt is nothing but your, this will be 2, will be going that 4 in the alpha L I can write down what, kg by Cp, can I not write down. So, kg by rho L Cp ln B plus 1, I can say this is C basically due to combustion, just to make that it is not due to vaporization, right, just to differentiate. B can be same, B can be used for combustion and vaporization, right. Of course, some kind of term will be eliminated when you are talking about combustion, and also vaporization, you will take care of that. So, therefore, I will have to basically now express this droplet diameter, right, in terms of d square, and that I can write down this as, I can write down 2d, right, I can do here itself, 2d is nothing but 2 into that, right. So, what I will be getting is basically d square is because I can take this inside, and dd square dt is equal to 8 kg by rho Cp ln B plus 1, right. And keep in mind that this I can call it as a k, right, k, and k is nothing but your 8 kg rho L Cp ln Bc plus 1, right. And if I integrate this equation 5, right, what I will get? I will get basically d square t is equal to d naught square minus kt, right. What is the right, how I am getting? Basically what I am doing, I am getting from this equation, I am getting d square is equal to minus kt plus c, right. With boundary condition t is equal to 0, what is d? D is equal to d naught. So, when this t is 0, this is d naught square is nothing but your c, right. Therefore, this is I can write down d square is equal to d naught square minus kt, right. This is the expression what I am getting, and this is a very simple relationship, right, and this is known as d square law. And people have also conducted experiment, they have observed for most of the single fuel droplet under quiescent atmosphere follows this one roughly. So, if you look at these are the k capital values, this is basically I can say this is there is some typographical error, this is capital K, right, this will be capital K, and these are calculated values from the simple analysis 9.3, whereas this is coming 8.14 and 14.2 is really not very far different, keeping in mind the simplicity of the analysis, right, that you can keep in mind. Now, if I plot this one, if I plot this thing, I will get d square by the time, and this is basically the droplet diameter, right. This is droplet burning time, this is droplet burning diameter. Now, you will have to evaluate this, how much time it will be taking. It looks to be linear, but actually it is not linear because it is goes by d square. So, therefore, you cannot really simply calculate, let us say 100 micron droplet, and it has gone, let us say 2 seconds, and then you are going for, let us say 1 mm droplet, and then this will, no, it is not that way. So, therefore, that has to be taken care, right, and this is very important to evaluate this TD. D naught is the initial diameter of droplet, right, and D is the diameter which will be changing, and it became 0 at time TD, right. So, that is the thing you should keep in mind, right. So, right, as I told earlier, d square varies linearly with time, and slope of plot is burning rate constant, and you can have some experimental data, you can have some people generally put some data here and then try to match this thing. These are, you can say, experimental data, right, need not to be this thing, there will be some scattered, and then you will have to say, okay, this is the which is matching, right, that way it is being done. So, we will take an example how to evaluate, right, this thing, and keep in mind that this is as I told earlier that it is very important to understand how one can do that, right, because of fact that the transfer number, although we have used quite complex relationship for finding estimating the transfer number, but that will not be affecting much the droplet burning rate. So, also the droplet lifetime, right, time lifetime of the droplet. Okay. So, and for that the properties which need to be looked at it. So, let us look at an example to illustrate that point. An hexane C16H14 droplet of diameter 200 micron is burnt in a combustors, like let us say 1 atmosphere pressure and T infinity 1300 Kelvin, and determine the lifetime of the single droplet, right. And keep in mind that of course the T adiabatic in this example should be given is something around 2200 Kelvin, right, and we will have to find out basically droplet lifetime, or some people got droplet burning time or the burning duration, time duration. So, we know that TD is basically D naught square by K, and D naught is already given, right. So, given is D naught is given is 200 micron meter, pressure is given 0.1 megapascal, T infinity is 1300 Kelvin, and T adiabatic is given. Okay. And what is K? K, this is burning rate constant, right, is equal to 8 kg by rho L Cp ln Bc plus 1. C I am using for combustion. Now, question arises how we will evaluate the properties of Kg and Cp, because as I told the Bc you can evaluate, using this formula. But here this properties has to be done properly, because this affect the burning constant Kg and Cp, right. Rho L anyway it will not be, because it is almost constant density of the liquid fuel. The generally if you look at the temperature will be varying. Let us say there is a droplet here, right. The flame will be little away from that, right. Let us say this is your flame surface. Now, the temperature, if I plot this temperature here, right, what will be, this will be something, temperature will be going up here, right, and then it will be receding. So, here it will be 2200 Kelvin, and ambient temperature here is something 1300 Kelvin. So, we will have to find out the properties. Now, properties, how I will have to find it out? I will have to use some approximation, right, because we are doing calculation. In numerical simulation, the properties will be changing along with the radial direction, right, it will be changing. But in our case, we cannot afford to do that, we will use some average properties, right. We will be evaluating properties, right, at average temperature, and that is what we will be doing 0.5 Tf flame temperature or adiabatic temperature. I can write adiabatic temperature, rather I should put flame temperature, because in some cases if it is given the flame temperature you can take. In this example we are using the adiabatic temperature, okay, plus the T B, right, we will be taking the Tb, and Tb is you can find out from the this thing, because we are using boiling temperature. The Tb is basically 342 Kelvin we are using. So, plus 342, I will be getting 1271 Kelvin. At this temperature I will be evaluating the thing, right. Now, question arises, you will be evaluating here, but the oxygen also having different properties, fuel is having different properties. What you will have to do? You will have to let us say gas thermal Kg, right, is to Kg of the mixture, right, you can say of the fuel air mixture at T average is to be evaluated, right. How we will do? We will be doing Kg is equal to 0.4 Kf, right, plus 0.6 K oxidizer. Keep in mind that this relationship is not very sacrosanct, you can use some different thing, but lot of people have used this approximation we are doing. Instead of 0.4 I can say, look, I will be using maybe 0.3 and then 0.7 the other one, that can be done, but people have used, so therefore we are using this. Now, each one of them Kf and Kox will be evaluated at what? At this temperature 1271 Kelvin. Now, these values is not given, but you can get in the some table, right. I will be using directly now 4 into 0.18 for Kf plus 0.6 into 0.08. Oxidizer here basically air, and that happens to be 0.12 watt per meter Kelvin, right. And similarly, Cp you will have to also evaluate, but Cp what we are taking is basically the fuel, right. Cpf we are considering, of course, F we are considering as 1.19 kilojoule per kg and Kelvin at T average 1271 Kelvin. Otherwise, similar formula can be done, but in this example I am just taking that way. right. What I am saying, there is another way of doing it, like in the similar way I can write down Cp is basically 0.4 Cp F plus 0.6 Cp of oxidizer. I can do that, but I have just taken for the simplicity, right. This can also be done. Are you getting? And at T average is equal to 1271 Kelvin. In this example, I am using this thing. Okay. So, now delta HV is also should be given, or you will have to find out from the data table, that is your 316 kilojoule per kg, and the heat of combustion has to be given, delta SC is equal to 45,000 that is kilojoule per kg, right. So, what we will have to do, we will have to basically evaluate the V, the transport number. This we can use any one of them, but we are using OXT is equal to Cp T infinity minus Ts plus delta Sc F Y oxidation infinity divided by delta HV, right. So, T infinity is given, this is given, you have already evaluated Cp. So, you can find out this thing, right. You can find out delta Sc is given, and Y oxygen infinity is known to you, right, and delta HV you can find it out, right. So, but you need to find out F, right, because this is you can find out from oxygen air what will be. So, then F has to be found out. F, for that you will have to use stoichiometric oxidizer, this is fuel, right, ratio, it is F is fuel oxidizer ratio, right, no? Okay, oxidizer fuel ratio you can write down nu as nu is equal to x plus y by 4.76 molecular weight of air. You can do other way around also, this is a direct formula I am using, and if you substitute these values you will get 15.16, that means F will be 1 by nu is nothing but your 0.0658, right. And what I will do, I will substitute all these values here, and when I do the substitute values, right, 1.19, this is 1300 minus 342 plus 45,000 into 0.0658 into 0.232, that is your oxidizer, right, divided by the 316, you will get something 5.78, right. And then from this you can find out basically K, right, by using this equation. I can say this is equation 1 and this is 2, by using equation 2 we can get basically K as 8 kg rho L Cp ln Bc plus 1, right. So, that will be 8 into 0.12, rho L is density is not given, but you know you will have to find out, that is 640 kg per meter cube, right, 6640 into 1190, right. Cp, this is kilojoule, I am putting in joule. So, right, this will be ln 5.78 plus 1, you will get a very small value, right, 10 power to minus 6 meter square per second. This is a meter square, so it will be very small. You can look at this burning rate constant. Then after that you will find out Td is basically d naught square by k, and this you will get is 0.017, right. So, when you substitute these values you will find it is a very small time, and this is second, okay. And if it is a droplet size is bigger, then it will take more time. Keep in mind that this is quiescent atmosphere, there might be turbulence, there might be flow which will be affecting the things, and also the droplet might be interacting, so the time will be different, you know. But however, as I told, it can be used as a design tool, right. So, till now we have discussed about basically under the quiescent atmosphere. Now we will see how we can utilize those relationships and look at to estimate the mass burning rate of the droplet when subjected to convective environment, right. So, that we will be looking at, because it is very important to do that from the practical point of view, right. So, because both the free and forced convection will be prevailing in the practical devices. So, for flow past a fuel, when you look at a droplet, flow past the fuel droplet, when its Reynolds number is greater than 20, this effect will be more predominant, and this Reynolds number is basically based on the diameter of the droplet, right. If I say this is basically RE d, rho V d by mu, right, and this you can say V infinity, this will be V infinity like which is having, right, that one can think of. So, if it is less than that, it will be not having much effect, that people have found out. So, then what will happen once it is greater than this, the front portion of the droplet will be like that, you know, it will be coming, and there is a boundary layer. This is of course your flame front, the temperature you can say thermal boundary layer, but there will be also aerodynamic boundary layer which I have not shown, and there is a wake region here. You know, there will be some kind of a vortices will be formed, particularly downstream of here, right, the droplet, okay, not that place, at least here, okay, not that far, okay. So, this region is very important, but we will be not considering this wake region, because this will be inherently 3-dimensional in nature, okay. So, therefore, that will be little difficult. What we will be looking at basically looking at the practical devices where the forced convection is more predominant, and what we will be doing, we will be looking at basically boundary condition, right, and then trying to look at how we can estimate those things by just twigging or rather applying the boundary condition at the droplet surface. So, if you look at what you will be, so this is the expression. If you look at SC is basically, if I look at the boundary condition, what will happening, this you know, like heat transfer, this is the heat transfer coefficient, right, SC into delta T, there will be some temperature. Let us look at this balance at the droplet surface we are looking at, where there will be some heat will be convected, right, because of the temperature gradient which will be there, and that is being convecting, that is affecting, that is SC. SC is basically convective heat transfer coefficient keep in mind that this I have taken average because this will be changing, right, and delta T is the temperature gradient with which the heat will be convected, right, that is the thing, and we will see how we can get the delta T. If you look at this term, then is equal to the mass flux at the surface, and this is nothing but your m dot f at surface into delta Hb, that is the heat of vaporization, right, is equal to basically same thing, the mass of the mass consumption of the fuel at the surface into the surface area, right, that is nothing but that, and that we have already seen, that is nothing but this expression is rho alpha L Rs ln 1 plus B C. I can say this is for combustion, right, into delta Hb. See, this is we are using quiescent atmosphere and trying to connect to the heat convected due to the forced convection. That is the thing what we are trying to do. And this delta T, if you look at, basically delta T is nothing but your F stoichiometric Y oxygen at the infinity delta Sc divided by Cp, right. This is the amount of heat which will be generated due to what? Due to flame front, and this is the heat which will be coming from this Ts to this thing, that will be also convected. So, therefore, you can this is the driving potential, because this is the driving potential for convective heat transfer, because without temperature gradient you cannot have convective heat transfer. So, therefore, that is, and you keep in mind that by increasing the T, right, due to the chemical reactions, you can really enhance the mass congestion of the droplet. Like if temperature of the flame is higher, then naturally what will happen? More heat will be transferred, and then because of convection it will be reaching, and then it will be affecting the droplet burning rate, right. So, what we will do? We will basically look at, this is equation 1. Now, we will substitute this delta T in this equation 1, right, and combine these two expression, what I will get? I am basically writing down these things, right. F stoichiometric as delta Sc into Cp, and then divided by Cp is equal to this. And if you look at, I can write down this term like as a little different way, but before doing that, let me tell you that this is basically a smaller term, right. It is quite small as compared to this term, the left hand. This is due to the combustion, the heat release is very high. So, I can write down that basically this as, this will be kind of a also the B, right. So, this will be, if I look at this, what I can write down this as basically F stoichiometric Y oxidizer infinity delta Sc, if that is 0, then divided by Cp, right. This is the term what it would be, and right. So, of course, I can do if it is approximately, but however, we can write down this expression as little different form, that is Sc average Rs by this is Kg, right. If I take this, I will be getting, because this alpha, this one is nothing but your Kg by Cp, right. So, this rho alpha is Kg by Cp. So, it will cancel it out. So, Kg will come, and then I will get is equal to ln B plus 1, right, divided by, this is the term, right, F stoichiometric, I am retaining the whole term delta Sc plus Cp T infinity minus T this thing, and keep in mind that divided by delta Hb. This you will find it is basically similar to the B, right. This term you can see is basically B number. So, I can write down this is ln B plus 1 divided by B, and keep in mind that this, can you say what is that? This is basically Nusselt number, right, based on what? Based on Rs. If I say this is based on Rs, this is nothing but your Nusselt number. So, I can write down this expression as Nu Rs is equal to basically ln b plus 1 divided by b is a very simple expression what we are just deriving for by balancing. Okay. So, we will stop over here. In the next lecture we will be discussing little bit about this thing, and then we will be moving to some other topic. Okay. Thank you very much.